Hello everybody, thanks for tuning in. My name is Philipp Hillger, and in this little video I'd like to introduce you to the research that we do in the Devices and Circuits group, which is part of the Institute for High Frequency and Communication Technology, led by Professor Pfeiffer at the University of Wuppertal in Germany. So in this group we are investigating aspects of circuit design and the design of on-chip electromagnetics to improve the performance of ICs that operate at the boundary of what is possible, frequency-wise. So our goal is to build THz ICs. That means ICs operating at 300 GHz and above in pretty much conventional RF CMOS technology or in high-speed SiGe-HBT technology. Let's start with a classification of the research that we do at the IHCT in the whole field of terahertz technology, based on this cost and performance trade-off plot shown here. In the top right quadrant, we have today's terahertz systems. Today's terahertz systems are usually based on custom high-performance technology platforms, such as 3.5 semiconductors, in which we can achieve cutoff frequencies of a terahertz and above, so really high cutoff frequencies, or these systems are based on photonic methods. So with these technologies, we can achieve very high performance. Traditionally, this meant in the terahertz range that we can provide some functionality at all in this frequency range. However, these systems have very high cost and they are also very bulky usually. And that means that they can mostly be only applied in niche applications. And with the research in silicon integration, we want to change that. So we want to build integrated terahertz systems that can in general address a much wider application space, where also large volume markets and large volume applications are included, so that terahertz technology can finally have also like significant economic and societal impact. So when it comes to advancing silicon integrated terahertz systems and their capability, there are really two key research areas. The first one is research in the technology itself, meaning in the speed of the integrated silicon devices. So what you can see here is the technology evolution of SiGe-HBT technology over the last years, which was mainly driven by the commercial interest into millimeter wave communication and radar systems. So I want to put the focus here on the research in the last decade, where we have the big funded projects, milestone projects, .5 and .7, which basically were the gate openers for silicon integrated terahertz circuits in SiGe-HBT technology, because here we were basically able to achieve maximum cutoff frequencies which go deep into the terahertz range. So in the .5 project, on the research level, there was 500 GHz Fmax achieved, which is now also commercially available. And in the .7 project, which represents the 5th generation of SiGe-HBT technology, there was even 700 GHz Fmax achieved. And although we are not directly involved with fabricating the devices themselves at the IHCT, what we do here is building benchmarking circuits. So in all these AU projects, we helped in building circuits like power amplifiers, low noise amplifiers, or even complete chipsets, for example, for communication, or chips for radar imaging, to benchmark the devices and the technology for the practical use. But when looking at the numbers here, it's clear that we cannot only wait for technology evolution itself to solve the problems of integrating high-performance silicon integrated terahertz systems. So with an Fmax of around 700 GHz available now, we are barely able to build circuits that operate fundamentally at the terahertz range, at the lower end of the terahertz range. So one really has to come up with some innovative circuit ideas and also some circuit approaches that are quite unique to the terahertz range to build capable terahertz ICs. And this is what we are mainly concerned with research-wise in this group Devices and Circuits. So one of these really important approaches that we are researching is the subharmonic operation of circuits. And what that means is sketched here in this figure. So traditional RF integrated circuits or millimeter wave integrated circuits are usually operated fundamentally. What that means is that they utilize only the first harmonic present in the system to realize the system functionality. In the terahertz frequency range, that really doesn't work out for ICs. So if we only have an Fmax available of around 500 GHz, it's clear that we have to use some kind of harmonic extraction and utilize higher order harmonics as compared to the fundamental to implement system functionality deeper into the terahertz range. For example, with an Fmax of 500 GHz, you would be able to implement an amplifier quite reliably at 165 GHz. And when you want to then go to 300 GHz and above, you would need to implement a doubler, for example. Or when you want to go to 650 GHz, you would need to implement a quadrupler and extract the fourth harmonic. So that may sound easy, but it really is not, especially since all the complexity of nonlinear system operation deep down to the device level is really involved in designing such subharmonically operated circuits. But there are also many other IC design challenges that keep us busy in this research group. And these are mostly related to the fact that the wavelength on the chip of our terahertz systems gets pretty close to what we have in terms of dimension of the chip scale itself. That means we have to consider high frequency effects everywhere, and basically all the designs are distributed systems. Even the micrometer scale interconnects that we have on the chip, for example, from a transistor to an antenna that is placed in the top layer of the technology, so the interconnect spans through the whole back end of line. So even these micrometer scale interconnects cause some considerable phase shifts. And this all calls for a really full custom design approach where high-speed transistors are co-integrated with on-chip passives. And electromagnetic design of planar circuits really becomes a key part of the whole design process. So what do we take away from this? In order to build terahertz ICs in the future that can be really employed in industry, we need to advance high-speed silicon technology, increase the speed of the silicon devices, and on the other hand, also we need to innovate in the field of terahertz circuit design. Both of these fields are researched at the IHCT. That means that we are investigating high-performance terahertz building blocks, including custom terahertz on-chip electromagnetic structures, such as filters, matching networks, or antennas. Then we're building efficient broadband circuits above 300 GHz, for example, power amplifiers, low noise amplifiers, or multiplier chains, and so on. And we are also investigating new ways of terahertz generation and detection. On the other hand, we are looking into system architectures that really try to utilize silicon technology and its advantages in terms of integration density and system complexity to counteract a little bit the low device speed that we are facing. And that may include building mixed signal terahertz circuits that co-integrate digital circuits with the terahertz front end to provide some system programmability or reconfigurability in a scalable circuits with lots of unit elements. And these systems may also have some advanced system functionality that can only be supplied in a largely scaled system, such as beam steering or beam forming. And in general, we are just looking into chip scale integration and packaging of terahertz ICs so that we can achieve integration levels that are quite comparable to conventional microelectronics. So let me finish this talk by showing you some micrographs of the chips that we have designed at the IHCT. The chips that you can see here on this slide are all integrated in 130 nanometers high-speed SiGe-HBT technology from IHP Microelectronics. However, at the IHCT, we are also investigating circuits based on modern RF CMOS technology, such as 22 nanometers FD-SOI. So, as visible, our research spans across a wide range of different circuit implementations, starting from the component level, where we have, for example, sources and terahertz detectors, which we are trying to optimize for radiated power and sensitivity, respectively. To more complex integrated systems, such as integrated radars for accurate positioning, biomedical sensors for applications in, for example, cancer diagnostics, or high-speed communication chipsets for future 6G communication. So if you want to know more about these different applications that we are addressing with our circuit design at the IHCT, I highly recommend to you to look into the other videos from the other research groups. In case you have any questions regarding the content of this video, please write an email to me at hilger@uni-wuppertal.de. And then that's it from my side, and thanks for your attention.